From a falling apple to the vast cosmic web, one invisible force pulls galaxies together, forms massive clusters, and stretches cosmic filaments across the universe. This force shapes the largest structures in existence, building the universe as we know it. Welcome to Mattermosaic, piecing together the universe, one discovery at a time. Gravity builds structure throughout the cosmos. It's the reason stars ignite when clouds of gas collapse under their own weight. It's what binds planets to their stars and keeps galaxies rotating as vast systems of billions of suns. But galaxies aren't islands in the void. They gather into enormous clusters, and those clusters connect into even larger superclusters, forming breathtaking patterns that span hundreds of millions of light-years. How did we uncover this grand cosmic architecture? The story starts in 1687 in London, when the brilliant mathematician and physicist Isaac Newton published his groundbreaking book, The Principia Mathematica. Newton proposed a revolutionary idea. Every object with mass attracts every other object in the universe. The strength of this attraction depends on how massive the objects are and how far apart they are. His law of universal gravitation, summarized in a simple yet powerful equation, was a triumph. For more than 2 centuries, it flawlessly explained the motion of the moon around the Earth, the planets around the sun, and even the paths of comets journeying through our solar system. But as telescopes grew more powerful in the early 20th century, astronomers began peering far beyond the Milky Way. They soon realized that gravity was sculpting structures far larger and more magnificent than Newton could have ever imagined. Then, in 1915, a new genius emerged. The German physicist Albert Einstein introduced a completely new way of thinking about gravity with his theory of general relativity. Einstein proposed that gravity isn't just a force between objects. Instead, massive objects literally bend the fabric of space and time itself. Matter simply moves along the curved paths created in this warped space-time. This mind-bending concept was dramatically confirmed in 1919. British astronomer Arthur Eddington led an expedition to the island of Principe off West Africa to observe a total solar eclipse. During the fleeting moments of darkness, his team measured the light from distant stars passing near the sun. Just as Einstein had predicted, the sun's immense gravity bent the starlight, shifting the star's apparent positions in the sky. It was a monumental victory for a new vision of the cosmos. Over the following decades, astronomers began the monumental task of mapping galaxies across vast regions of space. Observations from the iconic Mount Wilson Observatory in California revealed something astonishing. Galaxies weren't scattered randomly. Instead, they were clumped together, forming massive clusters bound by their mutual gravity. A great example nearby is the Virgo cluster. Located about 55 million light-years away, it contains over 1,000 galaxies, all dancing together in a shared gravitational field. These clusters themselves are not the end of the story. They connect into even more enormous structures called superclusters. Our own galaxy, the Milky Way, is part of the Laniakea supercluster, a colossal structure that spans roughly 520 million light-years and contains more than 100,000 galaxies. But as astronomers studied the motions of galaxies inside these clusters, they stumbled upon a major puzzle. In 1933, the Swiss astronomer Fritz Zwicky was examining galaxies in the Coma cluster. Using spectroscopic measurements, he calculated how fast they were orbiting the cluster's center. The results were shocking. The galaxies were moving far too quickly. The visible matter, all the stars and gas he could see, couldn't possibly generate enough gravity to hold the cluster together. According to the known laws of physics, the galaxies should have flown apart and dispersed long ago. Zwicky proposed a bold solution. Most of the cluster's mass must be completely invisible. He coined the term dark matter to describe this mysterious, unseen substance. Modern observations have overwhelmingly confirmed Zwicky's hypothesis. From the rotation speeds of individual galaxies to the way gravity bends light, and even the patterns in the afterglow of the Big Bang, all signs point to the same conclusion. Roughly 85% of all matter in the universe is dark matter. Although we can't see it, it provides the essential gravitational scaffolding that shapes the entire cosmic web. In the late 20th century, Powerful computer simulations brought this cosmic web to life. These simulations showed that dark matter forms immense, interconnected filaments stretching across hundreds of millions of light-years. Galaxies form and cluster along these filaments, like beads on a string, leaving vast, empty voids in between. Gravity on these cosmic scales can even bend light in a phenomenon called gravitational lensing. When light from a very distant galaxy passes near a massive cluster on its way to us, the cluster's gravity, mostly from dark matter, acts like a giant lens, bending and distorting the light's path. Images from the Hubble Space Telescope have captured spectacular arcs and rings of distorted light around galaxy clusters, giving us a way to map the otherwise invisible distribution of dark matter. More recently, the James Webb Space Telescope, launched in 2021, is using this same effect to study the very first galaxies that formed just a few 100 million years after the Big Bang, pushing our view deeper into cosmic history. Meanwhile, another cosmic discovery revealed that gravity isn't the only force shaping the universe on a grand scale. In 1929, American astronomer Edwin Hubble, also at Mount Wilson Observatory, discovered that distant galaxies are all moving away from us. More than that, the farther away a galaxy is, the faster it's receding. His measurements proved that the universe itself is expanding. This creates a cosmic tug-of-war. Gravity pulls matter together, trying to build ever larger structures, while the expansion of the universe pushes everything apart. Over billions of years, this delicate balance is what governs how cosmic structures grow and evolve into the intricate web we see today. The story of gravity begins with an apple falling to Earth and extends to the largest superclusters, stretching across hundreds of millions of light-years. It governs planets, stars, galaxies, and the invisible scaffolding of dark matter that holds it all together. Yet, profound questions remain. Scientists still don't know the exact nature of dark matter. Researchers are actively testing whether gravity itself might behave differently on the largest cosmic scales. Future telescopes and ambitious sky surveys promise to reveal new insights into these invisible structures and the forces that shape them. From the smallest falling objects to the immense architecture of clusters and superclusters, gravity remains the fundamental force connecting every scale of our universe. This is Mattermosaic, piecing together the universe, one discovery at a time. If this journey through gravity on the largest scales changed how you see the cosmos, share this video with someone curious about the forces shaping reality. And let us know in the comments which scientific mystery you want us to explore next. Thanks for watching.